Hello everybody, my name is Joseph, and today we're going to be covering roots of polynomial equations in episode 1 of my Precalculus series. What are roots? Roots are the values of x for a function, f of x, that makes f of x equal to 0. Roots are also known by these names: zeros, solutions, x-intercepts. There are two types of roots: real roots and complex roots. Real roots are x values that are real numbers that makes f of x equal to 0. Complex roots are x values that are complex numbers that make f of x equal to 0. There will be at most n roots for an nth degree polynomial. For example, a quadratic, which is a second degree polynomial, has at most 2 roots. The video will describe how to find any and all roots typically required for a pre-calculus class. Now, this video assumes that you have a basic understanding of Algebra 2. So there are certain concepts here that we're not going to fully go over, but I will briefly explain. If there's any question types not covered in this video that you see in the pre-calc class, let me know, and I will help. This is based off of what my school does and what I've seen many other schools do. So first degree polynomials, they take the form ax plus b equals 0. The reason why it's first degree is because the variable x's highest degree is 1. A and b are real numbers. Side note, the polynomials itself are just the ax plus b. To find the roots, you would set them equal to 0. And as this is a 1 degree polynomial, it only has one root. And the roots to these will always be real. There are two ways to find the roots: algebraically and graphically. For example, 6x plus 3 equals f of x. I'm just trying to move this out of the way. There we go. Move this over here for now. Algebraically, you can solve this like a regular two-step equation by setting f of x equal to 0, or you can realize that the general solution to any 1 degree polynomial is x equals negative b over a. This is derived for solving for x on the general form. If you were to take the general form highlighted up here in blue, ax plus b equals 0, and solve for x, you would get x equals negative b over a. Graphically, you can graph the equation and see what value of x crosses through the x-axis, in other terms, the x-intercept. So for this one, algebraically, if x equals negative b over a, then x would be negative 3 over 6, so negative 0.5. Graphically, I just used Desmos, you can see that f of x crosses the x-axis at x equals negative 0.5, so that is the root. Second degree polynomials take the form ax squared plus bx plus c equals f of x, where a, b, and c are real numbers. This equation can have either one real root, two real roots, or two complex roots. You cannot have one complex root. I will explain why later. The general solution to a quadratic equation is, and from Algebra 2 you should know this, x equals negative b plus or minus the square root of b squared minus 4c all over 2a. This is known as the quadratic formula. This is one of many ways to solve quadratic equations. Some others include graphing, factoring, completing the square, symmetry method, and many others. I won't go over all of them, but I am going to go into a little bit of detail about the quadratic formula, as that is crucial to help us solve second degree and even sometimes later third and fourth degree polynomials. The discriminant. The first step in using the quadratic formula is to find the discriminant. The discriminant is b squared minus 4ac. It is what is under the radical. The discriminant will tell you what type and how many roots there are. If the discriminant is positive, there are two real roots. If it is negative, there are two complex roots. If the discriminant is 0, then there is one root with multiplicity 2. And I'll show the image in a sec. If the discriminant is a perfect square, the roots will be rational. This is because the square root of any number that is not a perfect square is not rational. It is irrational. But if you take the square root of a perfect square, you will, of course, get a rational number. For example, the square root of 64, a perfect square, is 8, a rational number. Graphs of quadratics look like this. If it has two real roots, the graph of the quadratic will go through the x-axis twice. Notice here, this would be the graph of y equals x squared minus 4, and it is intercepting the x-axis at x equals negative 2 and x equals 2. When the quadratic has one real root, it will touch the x-axis at one point but not go through the x-axis. This would be the graph of y equals x minus 5 squared, in parentheses x minus 5, close parentheses, squared, in case it wasn't clear. Notice it just touching the x-axis, not becoming negative, not going below it like over here. And if a quadratic has two complex solutions, the graph will never touch or intersect the x-axis. So looking here, this would be the graph of each of these intervals vertically or 2. So this would be y equals x minus 5 squared plus 3. So this graph shifted up 3. As you can see, it never intersects the x-axis, so it must have two complex roots. Let's do a little bit of practice before we delve into some higher degree polynomials. I want you guys to find the discriminant and the roots of the following quadratic polynomials, and you're going to note the multiplicity of the roots if it is greater than 1. So, I give you guys a second to pause the video, and please try it out. Okay, I hope you've tried it out by now. Oh, no, never mind. I forgot to click them on. Please pause the video and try these polynomials now, and come back when you're ready. Okay, now we're ready to go. Starting with number 1. The discriminant, by plugging in the values for a, b, and c, is 64, which should tell you that it's two real solutions, and because 64 is a perfect square, two rational solutions, and that will make sense when you see the roots, x equals negative 3 and x equals 5. Both real and rational. Answer number 2. The discriminant in this case is 0, so if you remember, this will have one real root. So the root for this is x equals 3 with multiplicity of 2. Now this one, the discriminant is 56. It's positive, so it's going to have real roots. However, it is not a perfect square, therefore it will have irrational roots. As shown, we have x equals 2 plus the square root of 14 over 2, and x equals 2 minus the square root of 14 over 2. And for the last one, the discriminant is negative, which means we should have two complex roots, and as you see, we do here. 3 plus the square root of 3i over 2, and x equals 3 minus the square root of 3i over 2. Now we're going to introduce a greater concept which will help us solving higher degree polynomials, the fundamental theorem of polynomials, which states that every polynomial is a product of linear factors and or irreducible quadratics. This will be important when dealing with higher degree polynomials, like I said, and now let me show what I mean by that. But first, we have to cover some more topics to help us go over synthetic division. Synthetic division allows you to factor a polynomial easily once you know one root. For example, we know x squared minus 2x minus 15. We know x equals 5 is a root, and we want to find the other root. So, you might be saying, what is this chart? So I'm now going to explain synthetic division. So you make this little chart here with this L shape and then a line underneath here. And I always like to take note of the coefficients. So I write x squared, x, and then c. C stands for constant, and r over here stands for remainder. However, you're only dealing with remainders in very little scenarios. You don't need an r here normally. So if I was to divide this polynomial x squared minus 2x minus 15, I place the coefficients of each term here. So for x squared, the coefficient of x squared here is 1. So I'm going to place a 1. Then the coefficient of x is negative 2. I'm going to place a negative 2. The coefficient of the constant, or that's not a coefficient, it's just what the constant is negative 15. So what I'm going to do is the first step you do is you drop the 1 down here, and then you take whatever this number is here. I'll draw a line to make it clear. You're going to multiply these two numbers. So 1 1 times 5 is 5. So the 5 ends up here. Now, what you're going to do is you're going to add these two numbers. So negative 2 plus 5 is 3. Now you're going to repeat the process. You're going to multiply 3 by 5, and you're going to get 15. And then you're going to add negative 15 and 15 and get 0. This is our answer, 130. And now, the columns here are a little bit different. Basically, everything that's up here gets shifted over to the left. So like this, the x column gets moved to the left, the constant column comes to the left, and the remainder column comes to the left. This is our remainder of this division. The remainder is 0, and that'll tell us, yes. So down here, we know x plus 3 is a factor, so x equals negative 3 must be a root. This will make sense in a second. If 0 is the remainder, let's think about if we're just doing regular division. If I say like 64 divided by 8, that's 8. We all know that, and there's no remainder. If you divide a number by a number, and you get a number, or if you divide an integer by an integer, and you get an integer, that means that the divisor is a factor of the dividend, right? So in this case, it's the same thing. We divide it by the root, x equals 5. So now, since we got no remainder, we know obviously since before that x minus 5 is a factor. If you're a little bit confused on that, if x equals 5 is a root, then x minus 5 is going to make it equal to 0. Because if you plug in 5, that becomes 0. This, you should know from Algebra 2, will factor into x minus 5, x plus 3. Anything you plug here that makes this 0, the whole thing will be 0. But now, coming back to the synthetic division, what you do to find the results of this is you say, okay, so x has a coefficient of 1. X, the constant, coefficient of 3, plus 3. And there's no remainder, so so x plus 3, we know, must be a factor. And because x plus 3 is a factor, x equals negative 3 must be a root. You can also just be testing to see if a number is a root or not with synthetic division. For example, if you want to divide this, we can synthetically divide by negative 1. So again, let's go over this. You drop the number in the x squared column, or whatever the first column is, then you multiply it by the number up here. So 2 times negative 1 is negative 2, and then you add these two numbers. Negative 5 plus negative 2 is negative 7. Then you multiply negative 7 by this negative 1 up here. Again, you multiply the bottom number here by the number up here. Negative 7 times negative 1 is 7. Negative 7 plus 7 is 0. Because we have a remainder of 0, as explained before, that means that x equals negative 1 is a root, because x plus 1 is a factor. As I have down here, yeah, if that box is 0, that means there's no remainder when you divide by negative 1, which means x equals negative 1 is a root. And using from the result, the coefficient of the x term is 2, the constant term is negative 7, 2x minus 7 is a factor. So now we're going to cover some third degree polynomials. They take the standard form ax cubed plus bx squared plus cx plus d, where a, b, c, and d are all real numbers. In terms of factors, third degree polynomials will either have 4 separate types. And this is in terms of factors and roots as well. If a third degree polynomial has 3 real roots, its factors will be in the form like this, x minus m times x minus n times x minus p, 3 distinct linear factors. If the third degree polynomial has 2 real roots with one of the roots having a multiplicity of 2, it would be like this. Notice it's squared. It would have 2 linear factors and 1 being repeated. 1 real root with a multiplicity of 3, 1 twice repeated linear factor in this form. And if it has 1 real root and 2 complex roots, again, it would feature 1 linear factor like this and 1 irreducible quadratic. Now, this could not be broken up by any means of like regular factoring because they have complex roots. This is where I said that all third degree polynomials can be broken down into either a product of linear factors or irreducible quadratics. This is what I mean. Every single type you can have. These are all the root types, right here. And these are all the factor types you can have. Notice how there's no cubic that can't be broken down like that. Okay? So now the roots of a third degree polynomial, there's no easy formula for the roots of a cubic polynomial. There is a formula. However, I tried to put it into the slide. It was literally too big. You can Google it if you want. It's a very long formula. The problem is, because there's no formula, there are certain third degree polynomials that you won't be able to solve through the techniques used in precalculus. The way to find the roots of a third degree polynomial that you can solve is fittingly a three-step process. You need to find one root, synthetically divide by that root, and find the roots of the remaining quadratic. Let's break it down. Step 1, finding the first root. In order to find the first root of a third degree polynomial, you'll need to use something known as the rational root theorem. This will be very important, and I want you guys to be using this every single time you solve a cubic or, eventually when we get to them, quartics. For a cubic, notice the A and D highlighted. The rational root theorem says that if a polynomial has a rational root, notice the if, not every polynomial will, it will be of the form P over Q, where P is a factor of D and Q is a factor of A. For example, consider the third degree polynomial x cubed plus 5x squared plus 8x plus 4. The factors of the D, which in this case, so the constant term, is 4, is negative 1, 1, negative 2, 2, negative 4, and 4. Now, normally when you're used to seeing factors, you only list the positive ones. You must list the negative ones as well. That's why for 1, the coefficient of the x cubed term, or A, is negative 1 and 1. Now, we would divide all values of P by all values of D. In this case, though, you don't really have to. You can just divide by 1 and see that all the possible values of P and Q are this. And if you want to go ahead and check this, please feel free. Divide each of the factors of D by negative 1, and then divide them by 1. And you'll see they come out to the same thing. Now we have to test these factors using synthetic division to find the root of a cubic. In any pre-calc class, you'll never see a polynomial where the rational root theorem doesn't work unless they give you a specific root. Then you can skip the step because then you've found one root. Now finding one root and synthetic division. Let's try the synthetic division of it by x equals 1. As we do the synthetic division, reminder, now we have an x cubed column. 1 drops down, and then you multiply 1 by 1 up here, and you put the 1 in here. Then you add the 2. 5 plus 1 is 6. Then you take the 6, multiply it by the root 1. 6 times 1 is 6. You put the 6 here. 8 plus 6, 14. 14 times the root 1 is 14. 4 plus 14 is 18. 18 is not remainder 0, so as a synthetic division by x equals 1 does not have a result in a remainder of 0, it is not a root. That's how you know. If we were to do it by negative 1, though, you'll see by doing the synthetic division, which I'll go over one more time, x cubed has the 1, so you drop it down. 1 plus, you could put in a little, if you want to know why, you could put in a little 0 here if you wanted. 1 plus 0 is just 1. 1 times the negative 1, which is the root, is negative 1, so it comes here. 5 plus negative 1 is 4. 4 times negative 1 is negative 4. So then you're going to put it here. 8 plus negative 4 is 4. Then you're going to do 4 times the root negative 1, which is negative 4, and you see that there is a remainder of 0. So, as a result of the synthetic division by x equals negative 1, you get a remainder of 0. It's a root. This means that x plus 1 is a factor, and it also means by evaluating the result of the synthetic division, again, getting from this, this, and this, x squared plus 4x plus 4 is a factor. Again, if you're confused why, the x squared coefficient is 1, the 4 is the x coefficient, and the c is the constant term. Now we need to find the remaining roots. We've determined two factors here, and you can expand this out to check. And we know that x equals -1 as a root from this, but we must solve the quadratic equation to find the other roots. You can solve this quadratic any way you want. It's up to you. I choose to factor it. I'm going to factor this into x plus 2 squared and see that the other root is x equals -2 with a multiplicity of 2. So the roots of this equation are x equals -1 and x equals -2 with multiplicity 2. Its fully factored form is x plus 1 times x plus 2 squared. And that's how to find the roots of a cubic. Let's try it. Now, try this. I know I just went over how to do them, but take a minute, pause the video, see if you can. Alright, I hope you gave it your best shot. We're going to use, I don't know why everything just came up here, but to find the first root, remember we need to use the rational root theorem. So, we look at our constant term 6, this is our d, and we're going to go and we're going to list out all the factors. -1, 1, -2, 2, -3, 3, -6, 6, and then the factors of 1, our a term, is -1 over 1. So all of our possible roots is this list right here. Eventually, these lists are going to get really, really big, right? So I'm not going to be saying them all the time, and you're not going to have to, you don't even need to say them all the time. But it's important that you list all of them out because any one of them could be a root. Now, through synthetic division that we see x equals -3 is a root, and x squared plus 5x plus 2 is a factor. Again, to quickly go over it, you drop the 1 down. 1 times -3 is -3. We put it in here. Add these two. 8 plus -3 is 5. 5 times -3 is -15. 17 plus -15 is 2. -3 times 2 is -6. So, 6 plus -6 is 0. Since 0 is a remainder, x equals -3 is a root, which also means x plus 3 is a factor. And the result of this, 1x squared, so x squared, plus 5x plus 2 is a factor. Continuing the example, so we know that x squared plus 5x plus 2 is a factor, so we have to find the roots of that. I use the quadratic formula, do whatever method you want. The roots of it are square root of 17 minus 5 over 2 and negative square root of 17 minus 5 over 2. So overall, the roots of this equation are x equals -3, rad 17 minus 5 over 2, and negative rad 17 minus 5 over 2. Another one, try this on your own, and let me know when you've solved it. Pause the video. Okay, I assume you've given it a go. Some of you, if you really paid attention in Algebra 2, may notice you can factor this by grouping, which if you can, great. However, I do challenge you to solve this using the rational root theorem. So, our factors of -15 are -1, 1, -3, 3, -5, 5, -15, and 15. Factors of 1, -1, and 1. So these are our possible roots. And after trying out a few roots, you should see x equals 5 is a root. I'm not going to go through each time doing all of these to see which one is a root, but when you are doing it, you will. I'm just saving time. I don't want this to be a longer video than it already is. X equals 5 is a root. You can see the synthetic division here. Drop the 1. 1 times 5 is 5. -5 plus 5 is 0. 0 times 5 is 0. 3 plus 0 is 3. 3 times 5 is 15. -15 plus 5 is 0. This also means that x squared plus 3 is a factor. Because if you look, we have x squared plus 0x, so no x, plus 3. Continuing the example, so we know our cubic here factors into x minus 5 times x squared plus 3, and that x equals 5 as a root. So to find the remaining roots, I used our quadratic formula. Do whatever you want. Which when you find the roots of it, no matter how, you'll get rad 3i and negative rad 3i. Now, considering the two of these roots are complex, remember, that means that this third degree polynomial will only intercept the x-axis once, and that will be at x equals 5. Now, complex conjugate rule. Remember when I said that that you can't just have one complex root? Well, here's why. For a given polynomial, if the complex number a plus bi is a root, then its conjugate a minus bi must also be a root. This will allow us to solve for the roots of polynomials easier in situations like this. Consider this polynomial, x cubed minus 7x squared plus 9x minus 63. You are given that x equals 3i is a root, so you need to solve for the rest of the roots. Using the complex conjugate rule, if we know that x equals 3i is a root, which means that x equals negative 3i must also be a root, because you can kind of say that in terms of a plus bi form, x equals 3i is 0 plus 3i, so its conjugate form would be 0 minus 3i. So negative 3i would be a root. Which means that x plus 3i and x minus 3i are factors. So we can multiply them to find the irreducible quadratic that makes it up. Again, from Algebra 2 you should know how to do this, but I'm going to show all the steps in case you don't. Remember, you can use FOIL or whatever method you want. X times negative 3i, 3i times x, 3i times negative 3i, simplifies into x squared plus 9. So x squared plus 9 is a factor of x cubed minus 7x squared plus 9x minus 63. And you may have gotten that if you did factor by grouping. Again, this is just to show you how to solve proper cubics. Don't do factor by grouping. Now how will we find this remaining root? Or the remaining factor? We must use what is known as polynomial long division. Synthetic division is great when you want to divide a polynomial by a linear factor. So like x plus 3, x minus 5, whatever. But if you want to divide by a quadratic or anything bigger, you must use polynomial long division. For example, let's divide x squared minus 2x minus 15 by x minus 5. You can, again, as I know I said you have to use polynomial long division for things like a quadratic or bigger, but you can also do this for linear factors. I'm just trying to show what to do. This is very similar to long division, if you remember. So this is how you're going to do it. You're going to take this here. Make sure everything's in standard form, of course. And you're going to take this x squared and divide it by the first little term here, which is x. X squared divided by x is x. Now, to get this stuff down here, you're going to multiply this x by each of these terms. So x times x is x squared. Negative 5 times x is negative 5x. However, you're subtracting them, if you remember, from just long division. So this x squared becomes negative x squared, and this minus 5x becomes plus 5x. I highlighted where each of the terms came from just so you can see. Wanted to make it easy. Now you add what's left. X squared minus x squared is 0, which should happen. You should get 0 here. And negative 2x plus 5x is 3x. Now, just like regular long division, you drop the minus 15 and you divide. 3x, this term, goes into this x 3 times. So we write plus 3 up here. Then we multiply the 3 by this. 3x, 3 times x is 3x. But remember we're subtracting, so switch the sign. And then 3 times negative 5 is negative 15. Again, switch the sign, plus 15. We get a remainder of 0, which means it's a factor. Which means x minus 5 is a factor. But also that means x plus 3 is a factor. Which we know just from when you normally factor this, that x minus 5 and x plus 3 are factors. Now if we want to apply polynomial long division, here's what we can do. Important step in polynomial long division. X squared plus 9 does not have a 0x term in it. However, when you're doing polynomial long division, you must have it. So, same thing. This big term here, x cubed, we're going to divide it by the first term here, x squared. You just get x. Then you multiply this x to everything remaining. X times x squared is x cubed. Flip the sign because you're subtracting, you have negative x cubed. Then x times 0x is 0x squared. You can just keep 0x squared, it doesn't matter. I just flipped the sign to show. And then x times 9 is 9x. Flip the sign, remember, minus 9x. Now we add the two terms, x squared plus negative x, not x squared, x cubed plus negative x cubed is 0. Negative 7x squared plus 0x squared is negative 7x squared. 9x minus 9x is 0. And then you remember, just like long division, you bring this down. And you have negative 7x squared minus 63. Do the same process with this. Negative 7x squared divided by x squared is negative 7. Now you use this negative 7 and you multiply it by all of these, and you get your results here. Negative 7 times x squared is negative 7x squared, but flip the sign, it's plus 7x squared. Then you have negative 7 times 0x, which is just 0. Flip the sign, I'm doing it to just prove a point. Negative 7 times 9 is negative 63. Flip the sign, positive 63, you add these, triple zeros. This means x squared plus 9 is a factor, because when it divides by this polynomial, remainder 0. This also means that x minus 7 is a factor. Let's finish with the problem. We know x minus 7 is a factor, which means the full and complete factorization of this is x minus 7 times x minus 3i times x plus 3i, which means the roots of this are x equals 7, x equals 3i, and x minus 3i. Now, we've gone over to solve any cubics you see in your pre-calculus class. Remember, you'll always be given a root, or will be expected to use the rational root theorem to find one. Now, cortex. Fourth degree polynomials have the standard form ax to the fourth plus bx cubed plus cx squared plus dx plus e, where a, b, c, and d are real numbers. Let's go over this. There's a lot of different possibilities for cortex. Alright, but there's a little mistake here. Fix that. If a quartic has 4 real roots, it will have 4 distinct linear factors like this and 4 x-intercepts. If it has 3 real roots with 1 multiplicity 2, it will have 3 linear factors, 1 repeated, and 3 x-intercepts. It could also have 2 real roots, both having multiplicity 2. And it will be in the form of 2 repeated linear factors like this. Now, it could also have 2 real roots with 1 having multiplicity 3, so you'll have 1 twice repeated linear factor and 1 non-repeated linear factor. There could also be 2 real roots and 2 complex roots, meaning you could have 2 distinct linear factors and then an irreducible quadratic. All 3 of these have 2 x-intercepts. Now, if you have 1 real root with multiplicity 4, it will just be 1 thrice repeated linear factor. Now, if we have 1 real root with multiplicity 2 and 2 complex roots, we would have it like this, where there's 1 repeated linear factor and 1 irreducible quadratic, which signifies the 2 complex roots. Now, you could have 0 real roots and 2 complex roots with multiplicity 2. Again, this would be 2 conjugates being the root twice. It's very weird, you don't often see it, but it can happen. And then you could have no real roots and 4 complex roots, which have 2 separate irreducible quadratics. These 2 have 0 x-intercepts. Roots of a 4th degree polynomial are very similar to finding the roots of a 3rd degree polynomial. You use the rational root theorem to find a root. You'll not be required to solve any equations where the rational root theorem doesn't apply unless you're given the root. You're going to repeat step 1 for the resulting cubic, because when you use the rational root theorem to find the root, you're going to end up doing synthetic division. Right? So again, solving these big polynomials is just like you're breaking down a quartic into a cubic, and then a quadratic, and then you're just solving the quadratic. All solving any polynomial is breaking it down into smaller and smaller degrees. So let's do an example. Using the rational root theorem, I am going to be honest. I'm not going to say all these roots. I'll say the factors of 1, which is a, negative 1, and 1. So these are all possible roots. There's a lot of roots. I'm not going to go through all of them. If you want to practice synthetic division, though, please test them. The smallest root that works is x equals 2, as seen by the 0 in the remainder column. I'm not going to go over the synthetic division again, but feel free to pause and look through and see how the synthetic division worked. And you'll see that 0 in the remainder column means that x equals 2 is a root, x minus 2 is a factor, and the resulting cubic from this, x cubed plus 6x squared minus 19x minus 84, is also a factor. Solving the remaining cubic, we must again use the rational root theorem to determine another root. Once again, here are your possible roots. I am not going to do synthetic division on all of them. If you want some more practice, go ahead, do as many as you want. However, the root that works will be x equals negative 3. Here's a synthetic division for it. I'm not going to go over it again. You'll see 0 in the remainder column. This means that x equals negative 3 is a root, x plus 3 is a factor, and since the result of the synthetic division is x squared plus 3x minus 28, that means that x squared plus 3x minus 28 is a factor of x cubed plus 6x squared minus 19x minus 84, the resulting cubic, and by default, since x cubed plus 6 squared minus 19x minus 84 is a factor of this, the quadratic must also be a factor of this quartic. So, you could say that. To find the remaining roots, we must solve the quadratic that was created as a result of the synthetic division of the cubic. I choose to factor this like this. So this big quartic can be broken down into x plus 7 times x minus 4 times x plus 3 times x minus 2. So the roots of the quartic are x equals negative 7, x equals 4, x equals negative 3, x equals 2. Yeah. Remember, solving these polynomials are just about simplifying them. Let's do another example to try it on your own, and this one might be a bit complex. It's a math pun, don't worry. Try this out. Pause the video. Oh yeah. You're given that x minus 2i is a root. Solve for the other roots. Go from here. Pause the video. Remember your binomial conjugate theorem, or your complex conjugate theorem, and let me know and unpause the video when you're ready to solve. Okay, I hope you've tried it. Remember, we can apply the complex conjugate rule here. If a plus bi is a root, then a minus bi must be a root as well. So if x minus 2i is a root, that means x plus 2i must be a root as well, which means that the product of these two roots must be a factor. And through this expansion, we get x squared plus 4, which means x squared plus 4 must be a factor. Meaning we can use polynomial long... I spoiled it. We can divide this quartic by x squared plus 4, or we can use synthetic division or polynomial long division. Take your guesses. We're going to use polynomial long division, as I spoiled, because we are dividing by a polynomial that is not a linear factor. So I'll go over this one more time. You take the big number here, divided by this term. 2x to the fourth divided by x squared is 2x squared. Now you're going to take this 2x squared and you're going to multiply it to each term here. 2x squared times x squared is 2x to the fourth. However, switch signs. You're going to do the same thing for all these. 2x squared times 0x is 0x cubed. Switch the sign. And 2x squared times 4 is 8x squared, but switch the signs and then add. So add this, you get 0. Add this, you get negative x cubed. Add this, you get negative x squared. And then drop the negative 4x. Now we have this. We're going to take this term, divide it by negative x cubed. Take this negative x cubed, divide it by x squared. Negative x squared divided by x squared is negative x. Now we're going to take this negative x, multiply it to all of these terms. Negative x times x squared, negative x cubed. Switch the sign though, so x cubed. Negative x times 0x is 0x squared, switch the sign. Negative x times 4 is negative 4x, but switch the sign, so it's 4x. We're going to add this. These two cancel, so do these, and we're just left with negative x squared minus 4. And again, you will take this term, divide it by this term. Negative x squared divided by x squared is negative 1. Negative 1 results from multiplying it by these. You get 0. Since there's 0 as a remainder, 2x squared minus x minus 1 is a factor of the quartic. So we know that this quartic factors into x squared plus 4 times 2x squared minus x minus 1. This further can be simplified into this. Again, we know that these two are factors just from the beginning. So to find the rest of the roots, we must find the rest of the roots of this quadratic. I again choose the factor, but do whatever method you like the most. So this is me just fully factoring it, which means that our roots, by setting all these equal to 0 and solving, x equals negative 1/2, x equals 1, x equals negative 2i, and x equals 2i. If you're given a complex root, you won't have to use the rational root theorem at all. You just have to use polynomial long division. Personally, I find those easier, so I don't have to sit there and test a bunch of roots. This is the last example. You just need to find the roots. So you're going to have to use the rational root theorem for this one. Please pause the video, try it out, and let me know when you're done. Okay, I hope you are finished. Here we go. Let's start with the rational root theorem. Here are all the factors, and the possible roots are all of these. By the way, if you can't figure out all the factors of a number, the trick that I use is you can always go on to Desmos and type in, let's say you're trying to find the factors of, in this case, negative 32. You can type in xy equals negative 32 and look to see the points where there are integer solutions. That's how you know they're factors. So, again, you can practice synthetic division all you want. Go ahead, be my guest, the more the merrier. But I'm just going to tell you that one of the roots is x equals 2. And this is the synthetic division. Again, just the table, not going over this in much detail. I went over this a few times. Pause the video if you'd like to more understand this. To find the next root, because we know this factors into x minus 2 times x cubed plus x squared plus 16x plus 6, we find the other roots besides x equals 2, we must find the roots of the cubic. I challenge you, use synthetic division or polynomial long division, your choice, up to you, through the rational root theorem, not factor by grouping. I know you can, please don't. So the factors of 16 are this. For possible roots, these are all of our possible roots. Again, if you want more practice, you can try and use synthetic division on all of these. However, the one that works is x equals negative 1, as shown by this synthetic division. I don't know why this all popped up. Now we know that x to the 4th minus x squared plus 14x squared minus 16x minus 32 factors into x minus 2 times x plus 1 times x squared plus 16. To find the last two roots, you must find the roots of x squared plus 16. You can do this in any way you want, but I'll use difference of squares. There's a little trick that I use when I have something like this. Again, the square root of negative 16 is negative 4i and 4i, which means x to the 4th minus x cubed plus 14x squared minus 16x minus 32 will factor into x minus 2 times x plus 1 times x minus 4i times x plus 5. So the roots, x equals 2, x equals negative 1, x equals 4i, and x equals negative 4i. Thank you for watching. If you have any questions, please let me know. This should be all you need to know for any roots you need to solve for in your pre-calculus class. This is, again, more of the Algebra 3 portion. Hope you enjoyed. Please recommend me to people. Check out my channel. There's more videos on more topics. You can also go to my website if you would like tutoring. If you live in my area, which will be worked out when you book online. You can have in-person tutoring or you can have online tutoring. I offer both in a wide variety of subjects. So please feel free to check it out. Thank you for watching, and have a good one.